All right. Well, it's looking like it's about time. I only have six of you in here. Did anybody have any questions before we get started?
Will you be able to answer some questions after?
Yes. Yes.
Okay, cool.
No problem. All right. I was just looking back to see any particular problems that I thought were especially useful that I didn't do. And I don't really see much. There was one I skipped in the previous section, but I'm checking it now just to see. I think that one's not too bad. Y'all can do it on your own, but let's see. Yeah, 9-3 already did something like that. 9-4. Yeah, I'll go ahead and do that because I think I had neglected to do that last time. Let me see. Oh, I did do that one. Let's see. Okay. Yeah, go ahead and text me your first or chat me your first and last name if you haven't already. It looks like most of you have. So let's go ahead and get started. When we last met, we were in section, uh, basically the very next section. So 9-4 is what we were in. And I just want to recap. There's two examples at the bottom of that we should do. Section 9.3 was collision and impulse. And we talked a little bit about that. I didn't do an estimate problem, so I think I want to. It says, let's say this is supposed to be like example 9.6. I'm going to share this with you in a second, but I'm going to also get it started first. So let me go ahead and share my screen. I'm going to get this first problem started if I can. Okay, so your document should pop up in a second. Feel free to ask me questions as you're going along. Okay, so that's example 9.6 is what we're working. It basically says to estimate the average force delivered by a karate blow that breaks a board a few centimeters thick, assuming that the hand moves roughly at 10 meters per second when it hits the board. Okay, so what we have found is, well, let me go ahead and write this first. Estimate the average force of a, let's call it karate chop. I think that karate is probably supposed to be capitalized, but we're in physics, so I don't care. So karate chop. If the hand is moving at, let's say, 11.0 meters per second. So what we're going to try to say is basically the board is attempting to bring the hand to a stop. We're going to actually assume it does come to a stop. And I'm going to make use of some of the stuff we learned last time. Specifically, we had Newton's second law, which says the summation of the forces is actually equal to dp dt, where P is equal to mvr. P total could equal M1V1 plus M2V2 plus dot 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 for however many things we do. We also can introduce a concept called impulse. And the impulse, I didn't actually give you a symbol, though I did mention it the other day. The impulse is given a symbol J, and it is technically a vector quantity. And what it should be is either delta P, which equals the integral of dp from P initial to P final, like that, or it also equals the integral of the summation of the forces integrated over dt. But we can also reduce that to a approximate thing. So I'll say approximately equal to the total force average times delta t. So all of those are different ways to express the impulse. I don't know how I said impulse, but evidently that's a neat new word I just made up because I got stopped in the middle. So the impulse, I didn't give you the symbol last time, it's J. One meaning is that it's the actual change in momentum, the delta P, which means P final minus P initial. But again, it comes from Newton's second law where the summation of forces is equal to dP dt, and that could reduce to the summation of the forces on average is equal to delta P over delta T. So if you solve for delta P, which is the same thing as J, you'd get the summation of the forces on average times dt is equal to the change in momentum delta P, and both of them are J. So what we're going to do is we're going to go on the assumption that the mass of the hand is probably not unreasonable to assume the mass is 1.0 kilogram. We're going to assume that the velocity of the hand when it initially hits the board will be 11.0 meters per second, roughly. Again, just we're supposed to be estimating this, and what we're going to do is I'm going to first calculate J, which is delta P. And I'm doing this all in one dimension, so I can drop these vector symbols and just recognize a positive would be going in the positive direction of whatever axis I chose to point that direction, and negative would be the opposite direction. And in this case, delta P is P final minus P initial. What we're going to assume, like I said, is that the hand comes down with a full velocity of 11 meters per second and then comes to a stop in that small period of time, so that the final momentum is in fact zero and the initial momentum is the basically the 10 kilograms, or the 1 kilogram times the 11 meters per second. So we're going to say this is 0 minus pi, which is 1.0 kilograms, times 11.0 meters per second, which is clearly 11.0. That's one extra sig fig, and that is a Newton second. So that's our impulse. But our impulse is also equal to F average, which I'm leaving off the symbol, the sum of, because in this case, again, the board's just sitting perfectly still. It's sitting on cinder blocks. Gravity's pulling down on it. The cinder blocks are giving normal force that should cancel out the weight of gravity. And really, the any other forces on it would be really, really minuscule compared to the hit. So you can call this the summation of all the masses, or you can just realize that even if it wasn't the summation of all the forces, it's way bigger than any other forces acting on it. So I'm just going to substitute F average in place of the summation of the forces. And then that's all going to be computed by taking J and dividing it by delta P, or excuse me, delta T, because we found that J was F average uh, delta t. So we can actually say that J equals F average times delta t tells us that F average should be equal to J divided by delta t. Now the J we already figured out was technically it should have been a negative 11. The force is actually going to be in the negative direction because the change in momentum was supplied by the actual force applied from the board. The force from the board is going the opposite direction of the hand. So I'm going to call that force negative. So I'll put this 11.0 Newton seconds here. Looks like somebody just came in as well. And now I'm going to try to estimate what the time is. So you might say in general that the velocity, remember this formula, average velocity is equal to V0 plus V1 over t, and that's for constant acceleration. This is one of the equations we don't necessarily use that much, but it is really handy when we do use it, because you can just, assuming it's a constant acceleration, you can immediately come up with a average velocity. So in this case, I'm going to say the final velocity, of course, v1 was 0, and the initial velocity was 10 meters per second. So that means our v average would be 10 meter, or excuse me, it was 11 meters per second. Sorry about that. 11.0 meters per second plus 0 meters per second divided by 2. And of course, that gives us 6 point, well, half of 11 would be 5.5. So this is going to be 5.50 meters per second. That's the average velocity. Then V average is equal to distance divided by time, gives us a time which we'll call delta t, and that should be equal to the distance divided by the average velocity. I'm going to go ahead and say that the typical board is on the order of a single centimeter thick. And the picture they're using in there does look consistent with that. Maybe it's a centimeter and a half. Doesn't really matter too terribly much. I'm going to say about 1.25 times 10 to the negative 2 meters. So I'm basically saying that's 1.25 centimeters, because it clearly looks a little bigger than a centimeter, and probably is. And then the average time is going, or excuse me, the average velocity is going to be 5.50 meters per second. So if I take that 1.25 times 10 to the negative 2 and divide that by 5.50, that gives me 2.27. Actually, I should probably put it down here. That gives me 2.273 times 10 to the negative third seconds. We really only had maybe 2 sig figs, 3 sig figs on there. It looks like everything's going to be ultimately left to 2. So I'll just say this is 3 for right now. Now that I have that, I can plug this time, I can plug it right in here, and that should give me the force. So that's 2.273 times 10 to the negative third seconds. So I'm going to take my 11 and divide it by didn't mean to do that. Divide it by that, and that actually gives me 4,840 newtons. Obviously, I'm using way more than the number of sig figs, so I'm going to actually assume this is 2 sig figs, just to make up for the fact that the mass which was included was in fact 2 sig figs. So what we find is the average force when we're solving this is about 4.8 times 10 to the third newtons. Now, if you wanted to figure out what that was, that's about 2,000 pounds. Okay, so that's a pretty significant force, and yet we were able to calculate it as just an estimate. So that's the estimate of the force used to break the board. So I think that was pretty straightforward. Anybody have any questions on that? Notice how I made a lot of assumptions. I basically was using J over delta T was the average force, which I hadn't given you a symbol for J before, but I certainly told you how you could use that to calculate the average force. But I took a poke at saying, it's probably not unreasonable to assume a human arm can move as fast as 10, 11, 15 miles meters per second at most. I chose 11. I estimated the hand to be roughly a single kilogram, which is about 2.2 pounds. Obviously, it's a little bit different than that, but if you're just imagining modeling that the karate chop as a 2.2 pound ball moving at 11 meters per second, this is exactly the calculation you do. Assuming acceleration is constant is not necessarily very precise, but it does give us a step into the door so that we can solve the problem. So what I did was assume that the acceleration was constant. That allowed me to calculate an average velocity. That average velocity should be the distance divided by the time taken. But in this case, I'm going to use that average velocity and the distance to figure out how long the force actually acts so that you can break the board. So I took the distance to be roughly the thickness of a board, which I said was about 1.25 centimeters. And then I said the average velocity is the initial velocity, which was 11 meters per second, plus the final velocity, which is 0 meters per second, divided by 2. So that gave me the 5.5 meters per second. That gave me basically 2.27 milliseconds for the time. So all I had to do was take the impulse, which was 11 newtons, and divide it by the time, which is 2.273 times 10 to the negative third, and that gave me 4,840 newtons. It's really it's quite a bit more than 2,000 pounds. Remember, a newton's about actually no, a newton's about a quarter pound. So this should be on the order of 1,000 pounds at least, maybe 1,200, 1,300, something like that. So, anybody have any questions on that? All right, so that was a pretty straightforward problem using some of the stuff we used. I also last time had already given you some information, so let me restate that so we can make use of it. So, assuming the net external force is 0, then we know, oops, that dp dt is equal to 0, so p is equal to a constant. So if we assume we had two particles, let's say we have a particle right here, and we have another particle right here. This one's going to be a mass m sub a. Oops, that didn't turn out good at all. A mass m sub a, and this one has a mass m sub b. And what we're going to imagine is they're headed for a head-on collision. So this one is actually moving in the x direction at a velocity VA, and this one's moving in the negative x direction with a velocity VB. Okay, there's going to be a collision, at which time we're going to see something like this and something like this. And that's where they're colliding. And then sometime thereafter, oops, let's move that over to here. And now maybe I can shrink it back to the right size. So I'm going to say right about here, but that's not really the right size yet. So I'll make it right about there. It's supposed to be too tall, so Maybe that's good enough. Okay. And then we're going to have the other ball. It's also leaving the collision. This time it's leaving the collision horizontally, just like it came into the collision horizontally, but the final velocity is VA with a prime mark, and the final velocity for this one, again, also horizontal, is VB with a prime mark. That's the nomenclature that, or the symbology, I should say, that your book is using. So what we found from this, assuming the net external force is zero, we were able to basically say that MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Now that's for one dimension, but I can go ahead and say it's true in general for what I have there. If we assume 1D motion, and I'll say I period, E period, in other words, uh, a head-on collision, collision. If we assume that, then we can make it a little easier because everything's in one dimension, MAVA plus MBVB is equal to MAVA prime plus MBVB prime, like that. I'm going to call this equation 1. Now I'm going to make another statement. If the collision any collision is elastic, then K is also conserved. Okay. So when I set up this one, what we'll get is 1/2 M sub A V sub A squared plus 1/2 M sub B V sub B squared is equal to 1/2 M sub A V sub A prime squared plus 1/2 M sub B V sub B prime squared, like that. That is what I'm going to call equation 2. And that's true for any two bodies colliding, one dimension or not, because remember, kinetic energy is a scalar quantity. So you can sort of treat that V squared as V dot V if you wanted. But the main thing is we now have those two expressions. What I derived for you last time, I derived this for a head-on 1D collision. Well, I shouldn't say it. I want to leave the collision word off. I'm going to put it on the next line. 1D elastic collision in which the net external force is approximately zero. Okay, what we got from that was VA minus VB is equal to the negative of the negative of VA prime minus VB prime. Now, what that means, and I'm going to call this equation 3, what this means is that the difference in velocities before the collision and after the collision differ only by a negative sign. So I'm actually going to take off that box and I'm going to put a box in of a different color like this. So that's something we can use. But when we go to solve a problem, if it is one-dimensional and head-on and elastic, we can also use this one, which I've already used to derive 3, and we can use this one as well, which I've also already used to derive 3. But now I've got something that's a little simpler to use so we can solve very specific problems. So now that we have that, it would probably be helpful for me to show you some problems. So let's consider this is going to be another example, and this one's going to be like example 9-7. With this example, we have a pool ball uh, of mass m sub a is moving. Whoa, Nelly. Is moving with a speed VA and collides elastically with another identical pool ball. Oops. And I'd call that MB is equal to MA is just equal to plain M, right? Uh, what we're going to do is first off in part A, I'm going to say, what are the speeds of the two balls after the collision? Assuming they were both moving at VA and VB. And then part B, what if VB was 0? So that's my two questions. Does everybody somewhat follow this? So what I know is I have my conservation of energy equation, conservation momentum equation, and my conservation of kinetic energy equation. So I can make use of all that. In fact, I have 1/2 m sub a v sub a squared plus 1/2 m sub b v sub b squared is equal to 1/2 m sub a v sub a prime squared plus 1/2 m sub b v sub b prime squared. But the MA equals MB equals M causes me to be able to divide through by m, and all these masses will disappear. And then I'm also going to multiply through by 2 on both sides of the equation, which, as long as you do it to both sides, you're allowed to do. So ultimately, what this is going to give me is VA. Well, I should probably write it back in purple. This is going to give me a VA squared plus VB squared equals VA prime squared plus, and I really should have wrote that 2 a little higher so you wouldn't mistake it for a 12 being up there, plus VB prime squared. So this is basically the equivalent of our uh, conservation of kinetic energy, because all the mass is canceled out and the 1/2's canceled out. So I'll go ahead and call this equation 1. We're going to make use of that. We also have our equation 2, which we had already derived last time, which was basically VA minus VB is equal to the negative of VA prime minus VB prime, like that. And we could, of course, write that backwards too, and then just drop the negative. But think you can see what I get here. So that looks pretty good to help us. Now, if we try to add these two equations, let's say add equation 1 and I'll say equations 1 and 2. So VA squared. I did want to do that, right? Yeah. Oh, I got you. I got one more equation I got to put up there as well. So I'm not going to add 1 and 2. I'm going to add 2 and 3. So let me go ahead and correct that too. I was starting on a different part of the problem that I hadn't meant to. So finish this out. This is equation 2 and equation 3. The equation 3 is basically going to come from conservation of momentum, which, remember, is this equation right here. But once I get rid of all the m's, it just becomes VA plus VB equals VA prime plus VB prime. So I'm going to go ahead and write right here equation 3. And actually, it would have been better if I wrote it somewhere else, but I'll do it right here. It's not that big a deal. So I'm going to get VA plus VB is equal to VA prime plus VB prime. Now we can add those two, and it might help, for instance, to write this as VA minus VB equals VB prime minus VA prime, like that. And when we add those two, we get this. VA plus VA gives me 2VA. The VBs cancel out. And then I've got VA prime plus VB prime minus VA prime. So the VA primes are going to cancel each other out, but this time I get equals 2VB prime, like that. And because of that, we can now conclude that that VB prime is equal to just VA. So that's one expression of part of the answer for part A. But we also need to know what VA prime is. We're going on the assumption that we know VA and VB. So it's okay to have it in terms of VA or VB, but now we need to figure out what VB prime is, or VA prime is. In this case, I think we can just probably subtract the two. Yeah, let's subtract the two equations. So I'm going to say subtracting subtracting 1 and 3 gives us this. So this time I'm going to say VA minus VA plus VB. So in other words, I'm literally imagining multiplying through by a negative sign on the red equation here on the right. So I'm going to take that and multiply it by -1 and then add it. So I get VA minus VA because that negative is going to come in there. So that gives me 0, but I get VB plus VB. So this time I'm going to get 2VB is equal to, again, I'm multiplying through by a negative number here so that we can add them. So I'm going to get VA prime minus negative VA prime. That gives me 2 VA prime. I should probably write with the marker. And then if I subtract the other parts, I get VB, oops, did not mean to do that. That was supposed to be my laser pointer. I get VB, which is this guy right here, minus VB prime. So that gives me 0. And therefore, I now can say that VB or VA prime is actually going to be VB. So they're really just trading places, if you will. We'll say VA prime is actually equal to VB. I will box this off and say that is part B. So what we're imagining here is an example. Let's say 1.00 kilogram moving at 7.00 meters per second. And then there's a 1.00 because they have to have the same mass. And let's say now this one is 3.00 meters per second. That means that this is VA and this is VB. So this means after the collision, this ball will be moving at 3.00 meters per second, and this ball will be moving at 7.00 meters per second. So that's all it's saying is literally in a head-on collision, if they have the same mass, they're just going to trade velocities. You've probably done or seen something like this if you've ever seen Newton's cradle. Remember, Newton's cradle is sort of like a parallel bar and another parallel bar, and it's got these strings hanging down from each of the two parallel bars, and they hold a mass in the middle, and there's like 6 masses. So if you lift up one end like a pendulum, one mass on the end, and you drop it, it falls down, hits the line of masses, and just exactly one ball falls out and pops up to about the same height as you started with. It falls back down, hits that one, and repeats itself the other way. That's what we call Newton's cradle. And we're seeing that actually in action. If they happen to have the same mass, whatever the velocity is after, you'd expect the other one to come down or whatever. In this case, they're actually trading the difference in velocities, which is exactly what I called equation 3. That's exactly what that's doing. Now for part B, we can start looking for what about the VB equals 0 case. Well, if you did that, you could, again, I'm just ignoring I haven't even used the conservation of kinetic energy yet because I don't think we necessarily have to because we used it to come up with equation 2, which we are using. So the same thing's happening again, except now I've got equation 2 becomes VA equals negative VA prime plus VB prime. In other words, I just took equation 2 and substituted VB equals 0. Now I'm going to do the same thing with equation 3. And equation 3 was VA is equal to VA prime plus VB prime. So if I add those two equations, we can probably figure out something. So when I add them, I get 2VA is equal to, now in this case, you see the VA prime and the minus VA prime add together to give you 0, but the VB prime and the VB prime again add to give you 2VB prime. So what we found now is that VB prime is actually equal to VA. And I'm going to box this off with this color, and I'm going to say this is part B. Now I'm going to subtract 2 and 3. So I'm just imagining taking, for instance, the negative of all of equation 3 and then adding it to equation 2. So if I take the negative of equation 3, I'm going to get VA on the left-hand side from equation 2 minus VA on the left-hand side from equation 3. So that's going to give me 0. And then I'm going to take negative VA prime, that's from equation 2, minus negative or minus VA prime, that's for me crossing the negative. So that gives me negative 2 VA, 2 VA prime when I subtracted the 2. So that was negative VA prime minus VA prime. And then VB prime minus VB prime gives me 0. So this one tells me that, in fact, VA prime will just be 0. Now you see that in this case, since one was sitting still, this is exactly Newton's cradle. That's why when we drop the ball up here high, it'll come down, hit, and come to a stop. And then the other one would jump out. Now, if it was only two of them, you'd immediately see. But the nature of it is that if you put two of them or 50 of them there, probably to some extent, they might not be able to do all of 50. But either way, if you put some number there, if one comes in, one will pop out. If three come in, three will pop out. If two come in, two will pop out. But the main thing is the other one stops. So that's our results that we're getting. Anybody have any questions with that on that one? Now, if you've ever played pool, you know that a lot of times if you shoot a cue ball, you hit it, it hits like the 8 ball or the 9 ball or the 2 ball or whatever. The main thing is the white ball usually comes to a stop and the other ball takes off. That's this type of scenario because one of the balls was already not moving. Okay, so we've got that. Now let's do another one where this time we're not going to have equal masses. So this is more like example 9-8. So let's call this example 9-8. And again, it's more or less like the one in the book. I'm going to maybe change a little bit, but basically, what they're saying here, a very common practical situation is for a moving object MA to strike a second object MB, the target, at rest, so that VB initially is equal to 0. Also, the objects have unequal masses and the collision is elastic and occurs along a line head on. They want me to A, derive the equations for VB prime and VA prime in terms of the initial velocity VA and of mass MA and masses MA and MB. Determine the final velocities in part B if the moving object MA is much more massive than the target, and then in part C, do the same thing when MA is much smaller than the target. Okay, so we're imagining a head-on a head-on 1D collision such that only, whoa, M sub A is moving initially, and MB has VB equal to 0. It's the target. Okay, so that's a typical scenario. What I want to do is derive expressions for this. So derive VA prime and VB prime. So there's our problem. our solution is going to make use of some of our typical stuff. I'm going to start off with assuming that it's a head-on collision and the net external force is zero. What do they? Implies P is conserved. So with that in mind, that tells me that MA VA is equal to MA VA prime plus MB VB prime. Okay. And writing them all positive this way allows us to just derive the negative signs and stuff like that. So these variables only are a magnitude, have nothing to do with direction. Ultimately, when they get a negative assigned to it or positive, that's when we can actually assess direction. So that's one of the issues that we're doing. Uh, Imagine a head-on collision such that only, oh, it's also elastic collision. So since we're going on the assumption that it's elastic, I have in addition to equation one, I also have equation two, which would be 1/2 MA VA squared is equal to 1/2 MA VA prime squared plus 1/2 MB VB prime squared. I'll call that equation two. And we can actually make use of this. Specifically, if I take equation three, remember equation three, we had VA minus VB is equal to negative VA prime plus VB prime. That looks like about right to me. Yeah, that would be good. Yeah, I'm trying to remember what we actually had was actually VA minus VB is equal to negative VA prime minus VB prime. And if you distribute that negative and you let this go to zero and distribute this negative like such, then you just get VA is equal to negative VA prime plus VB prime. And that's what I'm showing there. Okay. So with that in mind, I can actually solve equation three. So solve equation three for VA prime. That gives me VA prime is actually equal to, notice if I pull it to the left, it's going to become positive, and then I'm going to get VB prime minus VA. Okay, so that's actually what's going to be our initial velocity, or excuse me, our particle A's velocity after the collision. So now that I have that, I can go ahead and plug that back into the conservation of energy equation. I'm going to call this equation four. Let's say plug, and actually I said energy, I meant momentum. Plug four into one. When I do that, I get MAVA is equal to MA times VB prime minus VA, and then plus MB prime, or excuse me, MB VB prime. So I can start manipulating it a little bit by just getting rid of the parentheses. So this will be MAVA is equal to MAVB prime minus MAVA plus MB VB prime like that. I can get all the VBs on the same side. That would be helpful, and get all the other variables on the other side. I'm going to do that by adding MA VA to both sides. And by doing that, I'm now going to have 2MA VA is equal to, now I have a VB term left in both of the terms, so, or a VB factor left in both terms. So I'm going to write VB prime out in front, and then I'm going to notice that this term gives me a MA, and that this term gives me a plus MB. So this is going to be plus MB like that. So now I can figure out what VB is, VB prime is. So VB prime is actually going to be equal to 2MA over MA plus MB times VA. Now, to me, this is a wonderful result because it looks just like one of the results we got from the Atwood machine. Remember when we did the Atwood machine, we found that the acceleration was one quantity and we found the tension in the string was another. And in the case of the tension in the string, we are in the tension in the string, what we found was basically the torque, or the tension, is equal to 2 M1 over M1 plus M2 times M2 times G. So basically what you see is it sort of looks like that. That's what I like about it, because it's easy for me to remember. And now I have a result for that. Now I can also plug this, which I will just say part A on there. I'm going to plug that into 4. So now I'm going to say plug this VB prime into equation 4. When I do that, I'm going to get VA prime is equal to VB prime, which we just found was 2MA over MA plus MB times VA, and then minus VA. So I can manipulate this a little bit, and that'll come in really handy. I can go ahead and call this VA prime, leave it right there. But I can also get a common denominator, and there is a common factor of VA, so I can pull this VA completely out in front. And now I'm going to say I have a 2MA on the numerator, but I have a MA plus MB for the denominator. And in order for me to get that, I have to multiply the negative VA by MA plus MB over MA plus MB. So this negative is going to become MA plus MB, or become basically in front of that. So does everybody follow the math I just did to get to this part? Anybody see any or not see how I got it, or need help? Well, I'm going to go ahead and distribute this. So I've got the VA, which I want to leave right there, but I want to distribute the negative through the actual numerator. So I've got 2MA minus MA, and then the negative also has to hit the MB, so it's minus MB, all that over MA plus MB, like that. So you can see that the 2MA minus MA is just going to give MA, and this looks even more like the Atwood machine, specifically the acceleration for the Atwood machine. We end up having that VA prime is actually equal to MA minus MB over MA plus MB, all of that times just VA. So that is the last part of part A, where we're just trying to figure out what the velocities of each of the particles would be after the collision. Does everybody follow that? Anybody have any questions? Okay. Now we can make use of these as well, because part B, they want us to assume one's really big and the other one's really small, and then they want us to do the opposite of it. So I'm going to do that, but I'm going to basically copy this over to the next page so I don't have to rewrite all the stuff, even though I really don't need all that I'm bringing. It's just a lot easier. So I'm going to say copy, copy, and now I'm going to go over here, make sure I didn't flip too far, and I'm just going to say paste. Paste. Now I didn't need all that crap, but I needed some of it. So now I'm going to go ahead and start erasing the stuff that I don't need, which was all of this. And I don't really need the, red and all that stuff. I don't need the boxes around it or anything like that. I just needed these two results. So that's what we have. So now, uh, let's say, what if MB is much, 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 much smaller than MA? Okay. What that means is this. I'm going to say VA prime, which is equal to MA minus MB over MA plus MB times VA. Okay. Now, what I want to do is be able to find a way where the MA getting really big could actually make some cancellations or something like that. So what I'm going to do is multiply top and bottom by 1 over MA. So I'm going to say 1 over MA over 1 over MA like that. And since I did it to top and bottom, I haven't changed the value here. So what I'm going to get is 1 minus MB over MA is all that's left in the numerator. And then the denominator, all that's left is 1 plus MB over MA. And then all of that, of course, is still being multiplied by VA. So you see, if I take the limit as MA becomes infinitely larger than MB, then what you're going to see is that the MB over MA term is just going to disappear in both parts of this, and I'm just going to get VA. So VA prime would equal the limit as, let's say, MA approaches infinity. Since I've got it in this ratio, we're not really concerned with it approaching infinity, but we are concerned with it approaching infinitely large compared to B. And since I did that division, it's okay to think of it this way. So I'm going to do 1 minus MB over MA over 1 plus MB over MA, and all that times VA. And that is clearly going to be just 1 minus 0 over 1 plus 0 times VA, which means VA prime is just going to be VA. So if the actual thing that's getting ready to collide is, let's say, a Mack truck hitting, let's say, a fly, then clearly the Mack truck is not going to slow down, and that's what we just saw here. But now we got to figure out what happens to the fly. Okay, so now I want to solve for the VB prime, and I'm going to do that now. So let's say VB prime. Oops, I'm using the wrong color. So VB prime is actually equal to the 2MA over MA plus MB. We're still considering this case, all that times VA. So I'm again going to multiply through by 1 over MA over 1 over MA. This is going to give me just a plain 2 on top, but it's going to give me a 1 plus MB over MA on the bottom, and then all that times VA. And then I'm going to say, again, the limit as MA approaches infinity. In this case, I'm going to get VB prime is equal to 2VA. So if you're the fly and a Mack truck comes flying at you at 60 miles per hour, the Mack truck is not going to be slowed down. Their velocity is going to remain the same, but your velocity is now going to be 120 miles per hour. So that's what happens. And I had something like this happen. I told my students about this just about every semester, but I was out running on the track at NC State, and I got kind of preoccupied because I saw a person on the other side of the track that didn't have any legs from like the above the knees down. He had those Blade Runner type legs, and he was running really fast. And I was like, man, that dude's fast. And I wanted to talk to him and find out how fast he could run a 40, all sorts of stuff. Well, then I finally decide I'm going to walk over and talk to him. And just as I get ready to walk, I hear a whoo, 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 and it's a big middle linebacker from the NC State football team, and he runs into the side of me. It hurt so bad, and I tried to hug him because I was afraid I was going to hurt this poor person. I'm used to being big. I was nothing compared to this poor guy, but I did urinate blood for a couple of days thereafter. So yay! Now let's try another collision. And this time we're going to, instead of saying the incoming particle is huge hitting a really small particle, which is what we just did, we're going to say, what if the incoming particle is really small? Okay. So what if MA is much, 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 much less than MB? Okay. So what I'm going to do is I'm going to take VA prime, which we know was which we know is MA minus MB over MA plus MB times VA. Now this time I'm going to multiply by MB, 1 over MB in the top and bottom. So I'm going to say 1 over MB over 1 over MB like that. When I do that, I get MA over MB minus 1 over MA over MB plus 1. And then all of that is times VA, which again, if I take the limit as, in this case, VB, or excuse me, MB. If I take the limit as MB goes to infinity, you can see that this is just going to be VA prime is going to be equal to negative VA. So it's literally going to bounce off of it at exactly the same speed. Of course, that's because of conservation of kinetic energy there, that you can see the initial speed had to be the final speed as well. Now we need to figure out what happens to the velocity of the thing that was hit. So this was, again, a case where the actual incoming projectile is really, really light, but it's hitting a really, really big thing. So we'd expect the really, really big thing not to feel much. So let's check out what VB prime is. So starting again with my purple, VB prime is supposed to be 2MA over MA plus MB times VA. Again, I'm going to multiply by 1 over mb. Yes, 1 over mb over 1 over mb, like this. This is going to give me 2 ma over mb divided by ma over mb plus 1. And then all of that, of course, is times VA. Okay. So now again, I'm going to take the limit as MB approaches infinity, which is not exactly what we're doing here, but I think you understand what I'm saying. So as MB gets really, really big, the MA over MB gets really, really small. So we're looking at something like 0 over 1 times VA. So ultimately what we have is VB prime is equal to 0. In other words, it's not going to move it. A parked Mack truck, for instance, is not going to be harmed by a fly hitting it. Any questions on that one? So yeah, this is also, by the way, the same math that makes it work really unhealthily for motorcycle riders. So you keep that physics in mind a little bit, not to scare you, just to remember that you're always at risk. So make sure you keep your eyes open and looking for people that aren't paying attention to you and that aren't doing what they're supposed to. Because as you can tell, if you're a motorcycle and you get hit by something like a car, your mass is insignificant even with your motorcycle compared to them. So now you got a projectile. Someone hits you going 60, you leave the bike going 120. That's not cool. So, anybody have any questions about that? All right, so that's a couple of neat little problems that we can work out, or that we were able to work out, and from it we've learned a little bit about collisions in general. You can go through this whole process again and make a derivation of the equations that you see on page 239. So I'm just going to remind you guys, see and read pages 239 and 240. Reason being is because the 239, which is often written at the bottom of a page, but it's sometimes written at the bottom, at the top of a page, is just in the middle of the page on this electronic ebook. And so I'm not sure if the equations I'm talking about for VB and VA prime are going to show up if you just go to 239. So that's what I want you to get from this, is a more general case where you can assume that both particles were moving and everything like that and still get a nice answer. So any questions on that? All right. Well, I'm going to, how much time we got? We still got about 12 minutes. Yeah, I guess we can do this one. I think that's about all we can do. So I'm going to do example 9 now. And basically this says a proton of mass 1.01 unified atomic mass unit is traveling at 3.60 times 10 to the fourth meters per second, has a head-on collision with a helium nucleus with an alpha particle. That's what an alpha particle is. It's a helium nucleus. So collision with an alpha particle, and I'll say M helium is equal to 4.00 unified atomic mass units initially at rest. Okay, this collision is elastic. And what we want to do is basically find out what the velocities of the proton and the helium nucleus are after the collision. So what I want to know is velocity alpha, which equals velocity helium. Okay. I want to know what that is, but I also want to know what the velocity of the proton is. So that's what we're trying to solve here. Now, this is an elastic collision. With no appreciable external force. F external. So because of that, we know that we can use our conservation of momentum. So we definitely have the mass of the proton times the velocity of the proton. That's hitting a dead target. So that's literally all of the momentum we have. I could, in fact, take the time to put +0 for the helium nucleus not moving initially. But then after that, we have a mass of the proton times the velocity of the proton after the collision, which is a Vp prime, plus the mass of the alpha particle times the velocity of the alpha particle prime, like that. So that's one of our equations we can use. I'm going to write one on it in case I need to use it later. And because the collision is elastic, we can also use the idea, remember, elastic and conserved momentum. That gave us VA minus VB is equal to negative VA prime minus VB prime, like that. But now that we have a VB equal to 0, we can just say VA is, or excuse me, yeah, we can just say VA is equal to negative VA prime plus VB prime. So in terms of our proton issue, what we have now is VP is equal to negative VP prime plus V alpha prime, like that. Everybody follow what we've done so far? So now I'm going to solve the second one, which I'm going to call equation 2. I'm going to solve that for VP prime. So VP prime is going to be equal to, if I pull it to the left-hand side and then pull the VP back to the other side, I'll get VB prime is equal to V alpha minus VP. Oh, that's V alpha prime. Sorry about that. Minus VP. Now, if I plug that into our equation 1, I'm going to call this 2 prime. Plug 2 prime into 1. When I do that, I get MP times VP is equal to MP times VP prime, but in this case, we're going to call it V alpha prime minus VP, like that. And then what was also left is plus M alpha V alpha prime. So you see now we only have one unknown, the V alpha prime. Let me distribute everything. That's going to give me, actually, I'll start it over here on this left a little further over. So MPVP is equal to MPV alpha prime minus MPVP plus M alpha V alpha prime. So I can now say that I have MP VP, and then if I pull that to the other side, that'll become plus MP VP. So that's this term right here has been pulled over there with this term. So that's why I got that. And now I have on the right hand side basically a V alpha in common with a MP plus M alpha times V alpha prime. Sorry, I in my excitement I mixed up an alpha with an A. That's not a good idea. So let me fix that and make sure y'all know it's an alpha. Okay, so now I have the ability to actually solve for V alpha. So V alpha prime is actually going to be equal to 2MP over M alpha plus MP times VP. So if I plug all this in, I can say 2 times. Notice I don't even have to change the masses because the conversion factor would cancel out anyways. But the main thing is you're going to see all the units for mass cancel out. The mass of the proton was 1.01 U. And then the mass of the alpha particle was 4.00 U, and the mass of the proton again was 1.01 U, and then the velocity of the proton was 3.60 times 10 to the fourth meters per second. So I can now say that, there I go with my A again, getting confused with an alpha. Didn't help that I used that as an example earlier, so that's probably coming back to roost. So there's my V alpha prime, but now I can finally solve for V alpha prime and say that it's actually 2 times 1.01 divided by parenthesis 4 plus 1.01 close parenthesis. That's 0.2015. I'm going to write that down just so y'all know. Whoa. Excuse me, I thought I hit 2 times 1.01, but I ended up hitting 1 times it. So let's do this again. 2, I obviously can do it in my head, but better than making a mistake. I'm going to say 2 times 1.01 divided by parentheses 4 plus 1.01 close parentheses. That should be 4030. Yep. So this quantity right here turns out to be 0.43 or 40319. That's the factor there. So now if I multiply that by 3.6 times 10 to the fourth, that gives me 1.4. Oops, I should probably write it in purple. That gives me 1.451 times 10 to the fourth meters per second. So the alpha particle will move at a markedly slower speed. Now we can figure out what the proton would do, what the proton would do, and that'd be V proton prime is equal to V alpha prime minus VP. So that's going to be 1.451 times 10 to the fourth meters per second minus 3.60 uh, times 10 to the fourth meters per second. Uh, Something went wrong with calculator. So I'm going to do that answer minus 3.6 times 10 to the 4. And that gives me VP prime. Notice we must have been assuming the alpha particle was moving in the positive direction. This one comes out to be moving in the negative direction, and it's negative 2.149. times 10 to the fourth meters per second, and that's our answer. Anybody have any questions on that one? All right, so that's it. Our time is up. Make sure you did chat me your first and last name if you hadn't already. I think everybody did though. But that's basically it. And I'm here to take questions until everybody needs to go. So I think Dylan had a question. You up for that, Dylan?
Yeah, I'm good.